One of the things I'll start out with is that as a geologist, you have a very different perspective on time. And I think a lot of people forget that. So the geology of Greensboro, we're going to be talking about that and how Greensboro and Caspian developed. But this is over a period of 500 million years. So this just didn't start yesterday. And I'm going to start out with periods of time. And on these periods of time, I've got a stratigraphic chart that gives us the ages of the events that led to the development of Greensboro and much of this part of Vermont. The important thing here is I'm going to first talk about a couple of concepts because I have an animation here that shows the development of the world, of the globe, as far as Greensboro. So we're talking about plate tectonics. So for the first 200 or 300 million years here, we've got pieces of the Earth moving around. We have rifting and ocean formation. The Rift Valley, this is like the Rift Valley in Africa. Things continue to spread apart. This is like the Red Sea. And then we have a larger ocean, and this is like the Atlantic Ocean. So here we are in the Atlantic side and how it developed. Now let's go over to when the continents come clashing together. This is called subduction and plate collision. In this case, we'll be talking about things like the tectonic mountains and subduction and movements of different parts of the plates on the globe. So we're going to start this at 540 million years, and it's going to take me a minute to get the animation going. But this is before the beginning of the deposition in the Ordovician. So we're here at the Cambrian, Precambrian boundary 540 million years ago. So this is a friend of mine put this together. This is plate tectonics and paleogeography through the ice ages. So this is the continents moving around beginning 504 million years ago. Here's North America, that's Baltica. And you can see things crashing into North America. And Greensboro's right about there. Now, this is the equator. So at this time, Greensboro was south of the equator. Now we're in the Devonian about 400 million years ago. At this point, North America is together, and it stays together. These other pieces keep moving around. 320 million years ago. So now we're getting into what's called the Mesozoic and the Permian, and we're forming a big continent here. And this was very dry through the middle. Those of you who've been out west, you see all the sand dunes that were out here. That's because it was dry, a desert. Now we're getting into the Jurassic and beginning getting into the age of the dinosaurs. And you can see North America, South America, Africa. So now we're in the lower Jurassic, 150 million years ago. The Atlantic is starting to open. Entering into about 130, 120 million years ago. Here's the South Atlantic opening. This is India, and you're going to see India crash up there. Late Cretaceous. And you can see India now just zooming up. Now we're in what's called the tertiary. The dinosaurs have died out, and now the mammals are proliferating. You can see India's now crashed, and that's the Himalaya. Now you're about to close this area and form the Caribbean and Central America. And then we get into the Ice Age, and then we get to today. So now we'll talk about what everything looks like today. And you can see a little red dot here, and that's Greensboro. And we're talking about a time about 490 million years ago, and these sediments were being deposited. These sediments you don't find in Greensboro, but if you go to the west of Elligo Lake, you'll start to see these sediments. There's a big difference between Greensboro and the area to the west. So we started out here about 490 million years ago, deposited these sediments, and these sediments were being deposited in this seaway here. And by 460 million years ago, there were some islands that crashed into North America, and it's what's called the tectonic orogeny. And that's everything you see west of Elligo. And there's a line that we call Cameron's Line that comes down, and I'll show you where that is in a little bit. 430 million years ago, you can see that ocean is still here, but you've got, this is Baltica, and Northern Europe, and this is parts of North America are crashing, and that ocean is closing. And this period here is the tectonic orogeny when there was no sediment. Now we're going to move on to the Silurian, and the Silurian is where we see the sediments in Greensboro. And in Greensboro, we really have three types of sediments that were deposited, and igneous rocks that were deposited during this period. We have the Waste River Formation, which is a meta-limestone. It's a slightly metamorphosed limestone, and that's the bulk of this area. There's some phyllite, which is a metamorphosed shale interbedded in it. And then there's some granite, or what we call granodiorite. And we'll talk about that in a minute, because that happens to come in up here. So at about 390 million years ago, between 460 and 390, we deposited the Waste River Formation. And that's followed by volcanism. And that volcanism, the remnants of that volcanism are plutons, and it's called the Craftsbury-Glover pluton. These are granites or granodiorites. They have quite a bit of variability. This is one, and the only place this is found is in Craftsbury. And these black areas are biotite, or a mica. And there's little orbs of mica that precipitate it. So when all of this came together, these mountains, as of 360 million years ago, may have been as high as the Himalaya. We don't know. We have no idea how high they were. But what we do know is they've been eroding for 360 million years. And the mountains themselves are the hills and mountains around here are the product of that erosion, and here you can see where Greensboro is, right on the edge of that. And these plutons are the underneath what were the volcanoes that were erupting during the Devonian period. So now we're going to skip from 360 million years ago to 75,000 years ago. There wasn't much happening around here except for the mountains eroding. 2.8 million years ago, you started to get glaciers. There's no evidence of those glaciers here now. What we see are the glaciers here in the late, what's called the late Pleistocene. That's a glacial period. And the glaciers were more than a mile thick here. And those glaciers extended, so this white line, it goes right through Long Island. That's how far south the glaciers went. So this whole area in the north was covered with very thick ice. This is what it looks like today. All of this was glaciers until about 12,000 years ago. Greensboro, about 13,000 years ago, that was the last of the ice. It's melted all the way back to Greenland, basically, today. So that's the time element that I'm talking about. Through 500 million years ago to today. This summarizes all of that went on in Greensboro, or in Vermont and New England. Here's the original plate. This is the Taconic Mountains. They come through here. This is what's called Cameron's Line, and here's Greensboro. So this actually is Precambrian rock. Then you have younger rocks here. We have our Silurian rocks over here with volcanic islands, and the sediments here were deposited in the ocean, deep oceans. Then these are remnants of pieces of Europe that were left behind when the Atlantic split up. Now let's start looking a little closer. So this is from the geologic map of Vermont, in the north half. This is Greensboro Township. The red crosshatched are the granites, granodiorites that were the remnants of the Acadian orogeny. The plutons that were left over from the volcanoes. This is Cameron's Line, and you can see a very big difference between the Waits River Formation here in blue and everything to the west, which was part of the Taconic orogeny. And these are much more highly deformed because they were deformed at the Taconics, and then when it crashed in, when this plate came in, it deformed them even more. So Greensboro has some of the Pluton, a lot of the Waits River Formation, and Cameron's Line goes right down the east side of Elligo Lake. A little closer look. Now this is the geologic map of Hardwick, the Hardwick Quadrangle. This is the Waits River Formation in beige. These are the Plutons. This particular Pluton is called the Craftsbury-Glover Pluton, and that's in Craftsbury, along the Black River, is where that granite occurs, that orbicular granite. Cameron's Line, and then these older sediments, and much more metamorphosed sediments than what we have here in Greensboro. We don't have any really good evidence for the age because we haven't found many fossils. Occasionally you'll find some little black carbon strips on a bedding plane, and that's probably a fossil, but we don't know. The only fossils I'm aware of near here, there was a fossil collecting trip near Irisburg back in the early 1900s, and all the fossils disappeared. They're no longer there. They're around somewhere, but they aren't there. This map was done in 1914. So we've gone from about 1965 to 1914. We've gone back in time here, but it displays very simply the geology. And I like this map because at that time, you could actually walk around the hills and see the rocks. You didn't have to worry about all these trees. This pattern are granites. Here's Black's Point. This is Cameron's Line, Elligo Pond, Caspian Lake, Long Pond, Paddock Hill. And what really got me interested in figuring this out was one day I was on a paddleboard out at the sunken island, and I was looking along the beds towards Black's Point. So I was standing here looking this way, and I saw some very interesting patterns. And I'll show you in a minute why when I found this paper, and that's a cross-section of what the Earth looks like along this line. So here's Bar Hill, here's Mount Sarah, just for reference. And what we see are a series of geologic structures along that line. Again, here's Mount Sarah for reference. Here's Bar Hill. And what I was looking at from the sunken island up towards Baker Hill was these vertical beds. Well, I confirmed it by going up Baker Hill. Since my son lives up there, it made it really easy, and found those beds, and yes, they are almost vertical. And here are the three types of rock. You've got the granite, the meta limestone, and the phyllite. Now let's put that together in today's context. So here's the map we were just looking at, oriented. And geologists are pretty fickle in that we like to have north at the top of the map. So that's north, and that's why it's skewed. This is what's called a LIDAR map. It's light detection and ranging. And you fly over the area, and you get very precise elevations. So here's Caspian, Greensboro Village. The island is here, here's Black's Point. So I was looking, and I was seeing these striations that I confirmed on the ground, and that's that syncline. This is Paddock Hill. This is Mount Sarah. And you can see the difference. Paddock Hill is the granite. Mount Sarah are the metasediments. So you can see the bedding here, and you don't see any bedding up there. Greensboro Bend is down here. This is Horse Pond, that's Mud Pond. So this, from a geologic structure, you can see things here, and we're going to talk about features here along the river in a few minutes. Because first I wanted to cover the geology of the bedrock, or as it's called around here, the ledge. It took me a while to figure that out, incidentally. And I'm going to go now into the Pleistocene and the glaciation. So this is the outline of the ice sheet 75,000 years ago that covered that entire area. Over here, I have the ice-covered area and the time going from 150,000 years ago to the present. So 150,000 years ago, which was before this map really, there was a cold and dry and ice covered. And these glaciers moved from the north to the south. Shortly after that, 130,000 years ago, it got quite a bit warmer. And these glaciers all melted over the 20 or 30,000 years. Then they started coming back. Here's the area of the ice. 75,000 years ago, which is when what we see today really happened and occurred and built, there was a lot of ice cover. And that extended to about 15,000 years ago, 14,500 years ago, and that's when the ice started to melt. The ice left the Greensboro area ice-free about 13,000 years ago. So what do we see from the glacial features? When the glaciers are moving, we have this glacial erosion, and we have glacial striations. So if we have bedrock here, there's striations. There are striations on top of Bar Hill. So here's abrasion and striations. If a glacier moves over a hill, you have let's call it the leeward side, down glacier. If it moves over a hill, it starts to pluck the rocks out, and it creates what's called a roche-moutonnaie, which is a sheep's back, and I'll show you an example of that in a minute. So this is glacier erosion. Then we have glacier deposition. Moraines. The moraine is a deposit at the front of the glacier. So the glacier stops, ice continues to move, it brings debris, and it piles up at the front of the glacier. And then the glacier will recede suddenly, and you'll build up another one. In front of the glacier, you have outwash plains. You have chunks of ice that the sediments are deposited around. When that ice melts, it leaves a hole called a kettle. Kames. A kame is a deposit of gravel, sand and gravel. I said last summer when I was here speaking, I said there was no gravel in Greensboro, or no sand and gravel deposit in Greensboro. Well, there's not. Very close, yes, but Greensboro's at the high, and these kames are with the glacier has a fissure, and the water flows down that fissure to the bottom. It takes sand and it builds this sand and gravel up. That's called a kame, and it also builds up terraces alongside the glacier. And of course, everywhere else there's till or ground moraine, and that's what makes up most of the soil around here. So I really want to talk about a little more detail, since we can relate to the last 10,000 years easier than the last 500 million years. Starting 13,000 years ago, high mountains were exposed and the ice retreats from Greensboro. Then things cooled off again. They warmed up again. By 12,000 years ago, northern Maine, Quebec, and New Brunswick were ice-free, or they had some ice, but not much. A period of cooling, and then again. So you had these climatic changes going on. So as you saw the ice retreat, it was also retreating in a series of climatic events. So 10,000 years ago was the beginning of the Holocene, which was that last map I showed you. At the beginning of the Holocene, climates got warmer. They were actually warmer than today. And it was moist. Then there was a cool period. 8,000 years ago, climates became warmer, moister, and these variations have occurred in the last, for that whole period down to today. So going back to geology rather than worrying about glaciers, so here's Greensboro, and I don't have any deposits mapped, which we call a superficial geology map of Greensboro because it's primarily till. But if we go into Craftsbury, all these streams have deposits in them of sand and gravel. There are terraces, there's kames, and that's where the gravel is focused that we use today in our roads. And that becomes very important. Also, there were lakes. There was a lake that came from Lake Winooski, came all the way up to Hardwick in the Lamoille River. And we find lake deposits there. So we have proglacial lakes, we have ice margin deposits, and that's the sand and gravel. We have stream terraces, and we have alluvium. Lots of different features, sediments from the glacier within these valleys. What do we see on the LiDAR maps? We see mountains like here at Paddock Hill, a very smooth back and a very steep front. So we know the glacier was flowing south. Same thing here, glacier flowing south. Gentle back and steep front. And that's the Roche-Moutonnaie. It's also a crag and tail is what it's called in some places. So we have the glaciated valleys, Long Pond, Caspian. Here's the main the river valley. There are kames outside of Greensboro. We see a lot of erratics. There are some kettles. Mud Pond may be a kettle. We see a lot of glacial erratics. We'll show you an example of that. And of course, we have glacial striae. I mentioned already that there's some on top of Bar Hill. Here you can see glacier flow direction, the crag and tail. This is a Roche Moutonnet, fairly smooth back and steep front. That's Buffalo Mountain. Some of you may understand where that picture was taken from. It's the third T. Glacial erratics. You've all seen big boulders in fields. This happens to be Rocking Rock. Pulpit Rock is another big glacial erratic. And there are glacial erratics all over that are quite large, and they, various sizes. And within the till is where we have to pick the rocks every year. So as a kid, every spring, we picked rock before we could do anything, because the rocks came up out of the ground every spring. So the glacier did a lot of eroding, left features behind, and I threw this in because I talked about the fact that we had 350 million years or 360 million years of erosion. It's still happening, and these are from last summer. These are called debris flows. We consider it a flood, but they're carrying all this debris, and so we call it a debris flow. And unfortunately, because we live in the mountains, this is what's the main erosive event that's been going on since the Devonian time. And we just have to plan for it and figure out how to handle it. I have no answers for that. Now, some of you may remember or may have heard about our Long Pond project that we started. I don't have many comments about that, but I've got a few here. We've not gotten very far on it yet. This is Long Pond, Paddock Hill up at the top. And here are, just for the view, I put a bathymetric map of Long Pond. This is north, incidentally. The wrong direction, and Long Pond itself is about 30 feet thick in the middle here. And what we did last summer, we took a shallow core here, we took another core down here. By coring, we drive a tube into the sediment. And we recover sediment, and I'll show you what we recovered, just to fill you in on what's happening there. This is part of the project. So we had this device floating on Long Pond. This is the core, a tripod that we use to hold the core. This is an example of one of the cores that we pulled out. I've been working on this project with Allison Stegner, Lori Grigg at Norwich, and Alexis, and I can never pronounce her last name, from Middlebury. So we've got a fair amount of coverage on it. This is what we pulled out, and what really struck me were these zones. Here's the top of the core. This is mud. And then you get this nice light stuff. Mud, again, nice light stuff. Well, it turns out this light stuff is marl. From a historical perspective, there are several lakes around that were, in the late 19th century, they would dredge the marl and put it on the fields because marl is calcium carbonate, so it's lime. And it helped their fields. I think, but I don't know where in Long Pond that they dug some of the marl out. But it's generated by calcareous algae. So the green algae actually causes calcium carbonate and then it drips into the sediment. So this is a very productive time here organically. So what are we trying to do with this information? Yeah, geologically this is fun because I got marl and mud and Can't get more happy than that, particularly if you're looking at the Pleistocene. This is an example from Ritterbush Pond near Belvedere. And why I started thinking about this at Long Pond had not been touched in, well, my entire period. There was no development around Long Pond. There was some in the 19th century, early 20th century. So I want a pristine area. Well, what are we looking for? This sort of thing is what intrigues me. So here we are, and we're using carbon-14 ages. We know that this is the glacial period ended about here, and you began to get sediment. What we're looking at is the proportions of different vegetations. Fir, spruce, pine, birch, oak, hemlock. What struck me on this one is the percentage of pine and the percentage of oak. Over a few thousand years, that was very high, and then the oak disappeared. Pine was very high, and then it disappeared. It didn't totally disappear, but became much less. So trying to understand what these changes in vegetation mean to historical climate. And that's what prompted me to get interested in it. So we'll be looking at the pollen data. We'll be looking at the chemistry. The chemistry of the sediments tells us about the chemistry of the waters and how these lakes developed over time. So this is just an update on our Long Pond project, and hopefully in the next year or so we'll get more results. The geology of Greensboro has always fascinated me. I used to find what I thought were likely lake sediments up on the top of the hill behind our house, and then I'd see the same kind of clays in Caspian Lake. I've always had an affinity for the Pleistocene. As a matter of fact, I have belonged to the Friends of the Pleistocene. But I hope this gives you an overview of the geology of Greensboro. We're talking about over 500 million years of development and changes in the earth, going from ocean bottoms to giant mountains to erosion to glaciers, and then the glaciers melting and leaving behind what we see today. So thank you very much, and I'll be happy to answer any questions.
My land seems to be two things, clay and ledge. What's clay?
Clay? Does it have rocks in it?
No, I'm blessed with not a lot of rocks. It's nothing like New Hampshire.
Well, the till is very clay.
Will you use a microphone?
Yeah.
Okay.
Yeah, the question is that our land seems to have a clay and ledge. And the clay is likely till.
Okay.
Unless, because, I'm talking, where's your land?
It's down towards Greensboro and about halfway down.
Okay, you may have some, actually that clay may actually be lake sediment, a side glacial lake. That's a possibility. I'd have to look at it to see, but there are lakes along the sides of the glacier, and it'll trap sediments. And then when the glacier melts, you have the sediment sitting there. Right nearby, you'll have ledge. Cameron's line.
Did that fault on?
No. Well, yeah, it's a joint of two different plates, yes.
And how active is that?
How active? Not active at all. Yeah, there's no danger. The only earthquakes you're going to get around here are you have over 5,000 feet of ice sitting on that depresses the land, and the land is still coming back. And the little earthquakes that we have periodically in New England, that's what those earthquakes are. Just rebound. Well, ice, if it's 5,000 feet thick, is plastic.
Okay.
So it'll flow.
So it'll flow.
So you put more snow on top, it compacts, and it pushes it out.
actually similar to this. On the Cameron's line, I think that slide that you had a very clear demarcation between the two areas geologically
Right.
of Vermont. One thing I was thinking about, so New Hampshire is often referred to as the granite state, granite staters. So would that mean that our geography in this particular part of Vermont and in Greensboro is much more similar to that of New Hampshire? Than
Yes.
it is? Okay.
Very simple answer on that one. Lynn?
So just to clarify, there are no longer any active subduction zones in New England. Is that what you're saying?
That is correct.
Okay.
Go to Indonesia, you got a different story.
Or New Mexico.
Or Mexico.
And Bob, just to be clear on something, when you use the phrase till,
Yes.
you're really just referring to, is that just loose sediment that's being washed down?
No, it's not being washed. It's the debris that's being ground down by the glacier and is at the bottom of that glacier. So when it leaves a layer of variable thickness, and because it's grinding everything, it's going to be quite fine, but it's going to have some sand in it. It's going to have rocks in it.
And are those rocks what you're referring to as the erratics, or are they at the front end of?
No, they're erratics because you get these big chunks like coming off of the front of one of these mountains. You have a big rock, and it gets entrained in the glacier, flows out with the glacier melts, it leaves it.
But wait, can I just follow up on that? So the stones that you picked every spring were not stones that were being pushed up from frost heaves that were part of the till. They were different kinds of stones.
No, they were in the till.
They were in the till. Okay.
What happens is that water expands when it freezes. It expands 9%. So every year, you get a little water underneath the rock. Rock is a good heat conductor or cold conductor. So it just pushes it up every year. And you get a new rock every year.
What caused the glaciers to melt and then come back? And was the sun doing something weird, or what?
Now we're getting into a very touchy subject, potentially. We do know that the climates were changing. What is the heat source for the Earth? Then it's the sun. And I do have a friend who he'll tell you very, very plainly that when the Arctic Ocean is ice-free, that's a source of moisture to be deposited on the land. So if that moisture then is able to freeze, eventually everything becomes covered with ice and you no longer have that source of moisture. I really don't know an answer. I do know a person who says that is the answer. But we do know that because the Earth's orbit is not circular, the Earth's angle is about 23.5 degrees. So if you move that around and you get farther away from the sun, that'll change the climate too, because you're farther from the sun. So Huckleberry rocks are right up in here, right?
Yeah.
If you look at this map, you see this granite, and that extends underneath Caspian. And so they are remnants of this granite that were not eroded deeply. So they're still at the level of the. I work with a group called Geoscientists Without Borders. We did have a project that we funded there, and what they determined was on the south coast of Java, if you feel the ground shake for 20 seconds, it's a significant earthquake. You have 20 minutes to get 20 meters high. because you're going to be, it's likely to be a tsunami coming in. 2020, and they use that now all over Indonesia.
So I was wondering about the marble that you see all over, in little stones and great big outcrops.
I mean here?
Yeah.
Actually, it's not marble, that's quartz.
It's not marble?
No,
Okay.
it won't dissolve. But what it is, when these plutons, or the magma that's in these plutons, as that magma cools, it leaves, you get the granite. But the very last fluids from those magmas are quartz-rich frequently, quartz, feldspar, and they're intruded. So right over here, on the corner of Church Lane, it's called a pegmatite. So that's that quartz vein, and you've got the Waits River Formation next to it, the meta limestone. So those, you'll see these white bands intruded through these rocks, and they're pegmatites that are a remnant of the fluids from the granites.
When's the glacier coming back to Greensboro?
I don't think we need to worry about it. A few generations hence, maybe.
Cameron's line, you said there were 2 plates that joined.
Yes.
What were the 2 plates? What were their names?
Well, one of them was, you had North America, or Laurentia, and then you had Baltica, and then you had these sediments, that's the Waits River Formation, that were being deposited in that ocean, and that's what we see here.
Do we know what made the pieces go together and then go apart?
Well, there's a couple of different theories. In part, it's pulling, but I showed that first slide of rifting.
Right.
Well, when it's rifting, you get like the mid-ocean ridge. There's magma underneath there, and it's active volcanoes. So the magma is coming up to the surface. And Iceland is right on the middle of that. And you can stand 1 foot on each plate in Iceland if you want, one in Europe and one in North America. The subduction part is a little more complex, but you do have a sinking, so the ocean sediment, or the ocean rock, is heavier than the continental rock. So you have basalt going underneath what's a relatively light granitic rock. And it descends, and then when it crashes together, that plate of the ocean is down now in the mantle.
I read that Long Pond is the headwater of the Lamoille.
Yes, that's one of
We
them.
should be very proud, but I've never seen that anywhere but once in 20 years.
Well, here's Long Pond, here's Lamoille.
That's a ways.
And that flows right down into the Lamoille, just as Caspian flows into the Moille down here.
Right, I knew about that part, but I didn't know about.
Well, the glacier obviously had an influence in the shape. Actually, the report that this map is in talks about the fact that there is a glacial moraine here at the end of Caspian. So you have a 140-foot depth here, and it comes to 0 depth there. But the water actually originally was dammed by a moraine.
Yeah, I read that.
Yeah, and the guys who did this report said you could take a shovel and dig that moraine out and drain part of Caspian if you wanted to. Yeah, probably one of the best examples of it came around here that I can use as an example is coming into East Hardwick. You know, you've got that big, that's a big came.
Yeah.
And that's what I'm talking about in terms of aggregate. You know, you've got small sand pits around, but nothing that compares to these big cames that are being used for aggregate. You know, you've got them on the road to Morrisville. You got them to the north also. Because remember, one of the things to remember here about Greensboro is where we are, everything goes south and towards Champlain. If you go north of Mount Sarah, everything's going north to Memphremagog. So we're on the top of the mountain. Any other questions? Well, thank you so much. This has been fun.